The National Electrical Code, specifically Section 250.118 requires a grounding electrode conductor, abbreviated GEC, for each separately derived system, abbreviated SDS. A separately derived system is defined as a system that is not supplied directly from a main service panel, nor from a transformer or generator that supplies other systems. Section 250.120c allows for a single GEC to be used for multiple separately derived systems when these systems are supplied from the same source and are located within the same building. Local authorities having jurisdiction, or OJs, may have additional stipulations regarding the grounding of separately derived systems. It is important to verify any local AHA requirements specific to the location. In this situation where you have two separately derived systems that are supplied from the same source and reside within the same building, National Electrical Code Section 250.120c dictates that one could run a single GEC from each separately derived system to grounding electrode, or alternatively, to the grounding electrode system of the building. This interpretation appears to align with the inspector's understanding of the NEC. The alternative argument is that only one GEC is needed due to the separately derived systems being interconnected through a single 2-inch ENT conduit. This stance also presents a valid interpretation of the NEC. Specifically, Section 250.118 does not delineate where the GEC must be connected, stipulating only that a GEC must be present for each SDS. To reconcile these differing interpretations, it is recommended to engage in a further discussion with the inspector. Provide a clear explanation of the interpretation of the NEC and offer a copy of Section 250.120c for reference. There is a possibility that the inspector will align with your interpretation and allow the implementation of a single GEC. Should the inspector not concur, the alternative is to proceed with installing a GEC from each separately derived system to the grounding electrode or the grounding electrode system of the building. The crucial aspect of grounding lies in its role in electrical safety. Grounding provides a low impedance path for fault current to return to the source. This low impedance path facilitates the quick operation of overcurrent protective devices such as circuit breakers or fuses, thereby minimizing the risk of electrical shock or fire. Effective grounding ensures that non-current carrying metallic parts of electrical equipment are maintained at or near ground potential, which further mitigates the risk of electrical shock. When installing grounding electrode conductors, several key factors need to be considered. Firstly, the size of the grounding electrode conductor must be adequate for the size of the service or separately derived system. NEC Table 250.66 provides guidance on the appropriate sizing of grounding electrode conductors based on the size of the service entrance conductors or the derived phase conductors. Secondly, the grounding electrode conductor must be securely connected to a grounding electrode. Acceptable grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The connection must be made using approved methods such as exothermic welding, listed lugs, or other approved connectors. Thirdly, the grounding electrode conductor must be installed in a manner that protects it from physical damage. If the conductor is exposed to physical damage, it should be installed in conduit or other suitable protective covering. Fourthly, the path of the grounding electrode conductor should be as short and direct as possible. Avoid unnecessary bends or loops in the conductor, as these can increase impedance and reduce the effectiveness of the grounding system. Lastly, it is important to ensure that all grounding connections are clean and tight. Loose or corroded connections can increase resistance and compromise the integrity of the grounding system. Regularly inspect grounding connections and tighten or replace them as needed. In the specific case of multiple separately derived systems fed through a single conduit, there are additional considerations. While the NEC allows for a single grounding electrode conductor to serve multiple separately derived systems under certain conditions, it is essential to ensure that the conductor is adequately sized to handle the combined fault current from all systems. The size of the grounding electrode conductor should be based on the largest service entrance conductor or derived phase conductor supplying any of the separately derived systems. Furthermore, it is important to consider the potential for circulating currents in the grounding system. When multiple separately derived systems are grounded at multiple points, circulating currents can develop due to differences in ground potential. These circulating currents can cause nuisance tripping of overcurrent protective devices and can also contribute to electromagnetic interference. To minimize circulating currents, it is generally recommended to ground separately derived systems at a single point. This can be achieved by bonding all of the separately derived systems to a common grounding electrode system. Another important consideration is the coordination of overcurrent protective devices. The overcurrent protective devices protecting the separately derived systems must be coordinated with the main service overcurrent protective device to ensure selective tripping. Selective tripping means that only the overcurrent protective device closest to the fault will trip, minimizing the disruption to the rest of the electrical system. To achieve selective tripping, the overcurrent protective devices must be sized and set appropriately. Coordination studies can be performed to determine the optimal settings for the overcurrent protective devices. In addition to the NEC requirements, there may be local codes or regulations that govern the grounding of separately derived systems. It is important to consult with the local authority having jurisdiction to determine if there are any specific requirements in your area. The local authority having jurisdiction may have additional requirements for grounding electrode conductor sizing, grounding electrode types, or grounding system installation methods. They may also require inspections of the grounding system to ensure compliance with local codes. Proper grounding is essential for electrical safety. By following the NEC requirements and consulting with the local authority having jurisdiction, you can ensure that your separately derived systems are properly grounded and that the risk of electrical shock or fire is minimized. Remember to always work with qualified electricians when installing or modifying electrical systems. Qualified electricians have the training and experience necessary to perform electrical work safely and in compliance with applicable codes and regulations. They can also help you to identify and address any potential grounding issues. Understanding the nuances of grounding systems requires a comprehensive knowledge of electrical theory, code requirements, and best practices. The grounding electrode conductor, or GEC, serves as a critical link between the electrical system and the earth, providing a low impedance path for fault currents. When dealing with multiple separately derived systems, abbreviated SDS, the NEC provides specific guidelines to ensure safety and proper function. Section 250.30 addresses grounding requirements for separately derived alternating current systems. A key aspect of this section is the location of the grounding electrode connection. For a separately derived system, the grounding electrode conductor connection must be made at the same point as the neutral conductor, typically at the source of the separately derived system. This ensures that the neutral and grounding systems are properly bonded, facilitating the flow of fault current back to the source. When multiple separately derived systems are supplied from the same source and located in the same building, the NEC allows for a common grounding electrode conductor. However, it's crucial to verify that the size of the common grounding electrode conductor is adequate to handle the combined fault current from all systems. The size of the conductor should be based on the largest service entrance conductor or derived phase conductor supplying any of the separately derived systems, as outlined in NEC Table 250.66. The grounding electrode itself must also meet specific requirements. Acceptable grounding electrodes include metal underground water pipes, metal frames of buildings, concrete encased electrodes, and ground rings. The electrode must be installed in accordance with NEC Section 250.52, which specifies the minimum burial depth, contact area, and other installation requirements. In addition to the grounding electrode conductor and the grounding electrode, the equipment grounding conductor, or EC, plays a vital role in the grounding system. The equipment grounding conductor provides a low impedance path for fault current to return to the source from non-current carrying metal parts of electrical equipment. The equipment grounding conductor must be sized in accordance with NEC Table 250.122, which is based on the rating of the overcurrent protective device protecting the circuit. When running multiple circuits in the same conduit, it's essential to ensure that each circuit has its own equipment grounding conductor. The equipment grounding conductors must be connected to the equipment grounding bus in the panel board or other distribution equipment. Bonding is another critical aspect of grounding. Bonding involves connecting all non-current carrying metal parts of the electrical system together to create a continuous electrical path. This includes metal conduits, metal enclosures, metal raceways, and metal equipment frames. Bonding helps to equalize the potential between different metal parts, reducing the risk of electrical shock. Bonding jumpers must be sized in accordance with NEC Table 250.102, which is based on the size of the circuit conductors. Surge protection is also an important consideration for separately derived systems. Surge protective devices, abbreviated SPD, are designed to protect electrical equipment from voltage surges caused by lightning, utility switching, or other events. SPD should be installed at the service entrance and at each separately derived system to provide comprehensive surge protection. The NEC provides specific requirements for the installation and wiring of SPD in Section 285. Coordination of overcurrent protective devices is another key aspect of electrical system design. Overcurrent protective devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. It's essential to coordinate the overcurrent protective devices so that only the device closest to the fault will trip, minimizing the disruption to the rest of the electrical system. Coordination studies can be performed to determine the optimal settings for the overcurrent protective devices. Ground fault protection is also an important safety feature for separately derived systems. Ground fault protection is designed to detect ground faults, which are unintentional connections between a phase conductor and ground. Ground fault protection devices, abbreviated GFP, will trip the circuit breaker when a ground fault is detected, preventing electrical shock and equipment damage. The NEC requires ground fault protection for certain types of equipment and installations, such as services rated 1000 amps or more. Electrical safety audits are a valuable tool for identifying potential grounding issues and ensuring compliance with the NEC. Electrical safety audits should be performed by qualified electrical inspectors or engineers. The audit should include a visual inspection of the electrical system, testing of grounding connections, and a review of electrical drawings and documentation. Proper documentation is essential for maintaining a safe and reliable electrical system. Electrical drawings, including single-line diagrams and panel schedules, should be kept up to date. Grounding system test reports should be retained for future reference. Maintenance is also critical for ensuring the continued effectiveness of the grounding system. Grounding connections should be inspected regularly and tightened or replaced as needed. Grounding electrodes should be tested periodically to verify their effectiveness. By following these best practices, you can ensure that your separately derived systems are properly grounded and that the risk of electrical shock or fire is minimized. Always consult with a qualified electrician or electrical engineer for assistance with grounding system design and installation. Remember that electrical work can be dangerous, so it's important to take all necessary safety precautions. Wear appropriate personal protective equipment, abbreviated PPE, such as gloves and safety glasses, to energize circuits before working on them. Use properly insulated tools, and follow all applicable safety regulations. Electrical safety is everyone's responsibility. By working together, we can create a safer electrical environment for ourselves and for others. Regularly inspect for damaged insulation. Ensure proper clearances around electrical equipment for adequate ventilation and safe operation. Verify that all electrical panels and enclosures are properly labeled with voltage and amperage ratings. Keep electrical panels and enclosures free from obstructions to allow for quick access in case of an emergency. Train personnel on basic electrical safety procedures, including how to identify potential hazards and how to respond in case of an electrical incident. Develop and implement an emergency action plan that outlines the steps to take in the event of an electrical emergency. Conduct regular safety meetings to discuss electrical safety topics and to reinforce safe work practices. Invest in high-quality electrical equipment and materials that are designed to meet or exceed industry safety standards. Perform routine maintenance on electrical equipment to prevent breakdowns and to ensure safe operation. Use lockout-tagout procedures when working on electrical equipment to prevent accidental energization. Use ground fault circuit interrupters, abbreviated GFCIs, in areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Install arc fault circuit interrupters, abbreviated FSIs, to protect against electrical fires caused by arc faults. Use surge suppressors to protect sensitive electronic equipment from voltage spikes. Use power conditioners to regulate voltage and to filter out electrical noise. Use uninterruptible power supplies, abbreviated UPS, to provide backup power in case of a power outage. Use appropriate wiring methods for the environment, such as conduit for exposed wiring and cable trays for large cable runs. Use proper grounding and bonding techniques to minimize the risk of electrical shock and fire. Use proper overcurrent protection to protect circuits from overloads and short circuits. Use proper voltage and current ratings for all electrical components. Use proper wire sizes for the load being served. Use proper torque specifications when tightening electrical connections. Use proper labeling for all electrical components and circuits. Use proper documentation for all electrical installations and modifications. Use proper training for all personnel who work on electrical equipment. Use proper personal protective equipment when working on electrical equipment. Use proper lockout-tagout procedures when working on electrical equipment. Use proper emergency procedures in case of an electrical incident. Always follow the National Electrical Code and all applicable local codes and regulations. Always consult with a qualified electrician or electrical engineer for assistance with electrical system design, installation, and maintenance. Remember that electrical safety is a continuous process that requires ongoing attention to detail and a commitment to safety. By following these guidelines, you can create a safer electrical environment for yourself, your family, and your community. The grounding system is critical in safeguarding against electrical hazards, ensuring that electrical equipment operates safely and effectively. The grounding electrode conductor, or GEC, plays a pivotal role by creating a low-impedance pathway for fault currents, which aids in the rapid tripping of overcurrent protection devices. Understanding the NEC requirements for separately derived systems, or SDS, is key to a safe installation. These regulations, found in Article 250 of the National Electrical Code, are intended to minimize electrical shock hazards and prevent damage to equipment. Key considerations include the location of the grounding electrode connection, the sizing of the GEC, and the types of permissible grounding electrodes. Proper documentation, including electrical drawings and grounding system test reports, is essential for maintaining a safe and reliable electrical system. It is always recommended to consult with qualified electrical professionals to ensure that the electrical system meets all safety requirements and operates effectively.